Hi, welcome back. I'm Professor Ronald Vincent Santiago, and today we'll be discussing Module 15, Case 1, Faults in an Unloaded Generator, Double Line to Ground Fault. What is a double line to ground fault? With a double line to ground fault, two line conductors come in contact both with each other and the ground. We'll assume these are phases B and C. In this diagram, we have phases B and C in contact and in contact to the ground through a fault impedance, say F. So, what are the boundary conditions? IA, this faulted condition, is equal to 0, BBG is equal to BCG equal to, say F multiplied by the currents IB plus IC. From the current relationships, we can now compute for the phase currents to be equal to the product of the A matrix and the phase currents at the fault, sequence fault currents. Now, since IA is equal to 0, we can say that the fault current, the sequence fault currents to be equal to 0. Note that because of the path to ground, the zero sequence current is no longer 0. From the voltage relationships, we can also get the sequence fault currents to be equal to 1/3 multiplied by the inverse of the A matrix and the phase voltages. Now, since BBG is equal to BCG, we can say that the fault positive sequence and the negative sequence of the voltage are equal. BBG is equal to voltage at the fault at zero sequence plus the quantity A square plus A multiplied by the voltage BF, positive sequence voltage BF. But since 1 plus A square is equal to 0 and A square plus A is equal to -1, we can say that BBG is equal to BF of the zero sequence minus the BF of the positive sequence. Having known that BBG is equal to the difference between the voltage during the zero sequence and the positive sequence, we can say that BBG is equal to ZF multiplied by the quantity IB plus IC. Also, since IB is equal to IF plus, for the zero sequence, plus A square, IF of the positive sequence plus A of the current multiplied by the current IF of the negative sequence. IC is equal to IF of the zero sequence plus A IF positive sequence plus A square IF of the negative sequence. Adding this together with A plus A square to be equal to -1, we can say that BBG is equal to CF multiplied by the quantity 2 multiplied by IF of the zero sequence minus IF of the positive sequence minus IF of the negative sequence, with IF of the zero sequence to be equal to negative IF of the positive sequence minus IF of the negative sequence. So thus, we can say that 3CF multiplied by the IF fault current of the zero sequence network is equal to the difference between the voltage of the zero sequence network and the positive sequence network. So thus, the interconnection now will be shown in this diagram. The three sequence networks are joined as follows, as shown in the diagram. Notice that the zero sequence network composed of C0 and in series with 3CF are in parallel with the negative sequence network, say 2. And this parallel interconnection or combination is in series with the positive sequence network, say 1 in series with E1. So assuming that CF in this system is equal to 0, we can now compute for the positive sequence current flowing to the positive sequence network. And that gives us to be equal to 4.547 angle of -90 degrees. Now, solving for the voltage, positive sequence voltage in that interconnection of the three sequence networks, BF is equal to 1.05 minus 4.547 angle of negative 90 degrees multiplied by J 0.1389 to be equal to 0.4184. The negative sequence current flowing to the negative sequence network is equal to negative 0.4184 divided by J 0.1456, and that gives us J 2.874. And for the current flowing to the zero sequence network, so that gives us negative IF of the positive sequence minus the current flowing to the negative sequence, and that gives us J 1.673. Converting this to phase, so that gives us IB equal to negative 1.04 plus J 6.82. IC now is equal to 1.04 plus J 6.82. That ends our module number 15. See you in our next module.